Hello, this is lecture 3, stat 134. Last time we covered section 1.4 and 1.5 and introduced mutually exclusive events, which means that they're disjoint or non-intersecting, and also independent events, which you really can't represent by a Venn diagram. Instead, it's defined by the multiplication rule being the probability of A and B is equal to the probability of A times the probability of B. We also talked about tree diagrams, and in particular, the first, so for example, having two phones and also determining whether the phone is good or bad dependent on whether you have phone 1 or phone 2. So Bayes' rule says that the probability that you have phone 1 given that it's good is the probability that you have phone 1 and that it's good divided by the probability that it's good. The probability that you have phone 1 or phone 2 is called a prior. It's the first step in your chain. And the probability that you have phone 1 given that it's good is called a posterior. It's also a probability about phone 1, just like the prior is, but it's a conditional probability. You have some data, you know that, for example, it's good. And by writing in different forms of Bayes' rule, the second form of Bayes' rule allows you to see that the posterior is proportional to the prior times the likelihood. So the likelihood is the probability of the second arrow in the chain. The proportionality constant is 1 over the probability of being good. And the probability of being good can be, it's a total probability. You can partition goodness according to whether it's goodness of phone 1 or goodness of phone 2. So here in this Venn diagram, I have phone 1 and 2 partitioning goodness so that I can write goodness as two mutually exclusive events, good in phone 1, good in phone 2, so that the probability of being good by the addition rule is the probability that you're good in phone 1 plus the probability that you're good in phone 2. And then the multiplication rule gives me the formula on the bottom. So today what we're going to do is we're going to finish Bayes' rule, and then we're just going to touch on section 1.6. You've already done the birthday problem in section. So we're just going to talk about independence versus pairwise independence for three events. So let's start with section 1.5, Bayes' rule. So here, 5% of the population has a disease. So in other words, the probability of D is 0.05. This is a prior. So they take a test, and either, so the probability of having a positive test given the disease is 0.99. The probability of having a negative test given that you don't have the disease is 0.95, and these are likelihoods. So one person's picked at random from the population. Given that the test is positive, what's the chance he has the disease? In other words, what's the probability that you have the disease given that it's positive? This is a posterior, right? And so the prior was 0.05. You would expect the posterior to be greater, right? If you find out that you have a positive test, it's more likely you have the disease. So we're going to make a tree. We're going to find the probability that you have a positive test, and then we're going to find the posterior. So we start off with our tree. The first chain in the tree is whether we have the disease or not, because that's our prior. And then we have our likelihoods for the second chain. And the probability that we have a positive test is the sum of the two highlighted branches. The posterior then is the ratio of the first branch over the sum of the two branches. And so indeed we see that the probability increases if you have a positive test. Then we did a concept test, and here, suppose A and B are two events with the probability of A being 0.5 and the probability of A union B being 0.8. Is it possible for A and B to be both mutually exclusive and independent? Well, most of the time the answer is no. In this case, because A union B is greater than 0.5, we know that the probability of B has to be greater than 0, and so if A and B are mutually exclusive, that means they're disjoint. In other words, the probability of A B is 0, and if you have independence, the probability of A B, which is 0, is equal to the probability of A times the probability of B, which implies that either A or B have to have probability 0, which is not the case here. So it's not possible to have both mutual exclusive and independent sets in this case. It is, however, possible to have two sets be mutually exclusive and independent, although very rare. An example is, for example, let A be the event that a person's 200 years old. That has probability A is 0. B be the event that a person is a female. So the probability that you're a 200-year-old female is 0. So A and B are mutually exclusive. And furthermore, since the probability of A is 0, the probability of AB is equal to the probability of A times the probability of B, so we do have independence. But this is a stupid example, obviously. This kind of thing is very rare. Recall from section 1.3 this example of these different shaped die. In this example, from the geometry of these die, if it lands flat, then it's equally likely to be a 1 or a 6. So this is a problem from section 1.5. A box contains 3 die, D1, D2, D3, with probabilities 1/3, 1/2, and 2/3, respectively, of landing flat. Right? So if the die is a perfect cube, that would be like D1, right? So the probability of landing flat, namely a 1 or a 6 on top, would be 1/3. So that's what we call a fair die when the die is a cube. Otherwise, it's a not fair cube. And part A, one of the 3 shapes will be drawn at random and rolled. What's the chance the number rolled is 6? B, given that 6 is rolled, what's the chance the fair die was chosen? So the question, so the probability that a fair die is chosen, in other words, the probability of D1, right, that's a prior, right? And so maybe it's helpful to make a little diagram here. So we have D1, D2, and D3 here, right? And because we're randomly drawing these out of a hat, they each have probability 1/3. That's our prior, right? And then we either get a 6 or not a 6. So we get a 6 or not a 6. 6 or not a 6. Right? And so what's the chance of the number rolled being a 6? So that's going to be the sum of these 3 branches here. Okay, that's going to be part A. And given that the 6 is rolled, what's the chance that a fair die was chosen? Okay, so So this is going to be the posterior, right, which is going to be the ratio of the top branch over the sum of the three branches. So we'll get to that in time. So let's see here. So for A, the probability that you roll a 6, given that you choose D1. So given that it is D1, the chance of landing flat is a third, so the chance of rolling a 6 is 1/2 times a third, or 1/6. And similarly for the others, we have 1/4 and 1/3. So then the probability of rolling a 6, that's the total probability. So that's the sum of the three branches, which turns out to be 0.25. And then for part B, the posterior here is the ratio of the top branch to the sum of the three branches. So that's 0.22, right? And this should make sense to you. So initially the prior was 1/3, and you roll a 6, right? So rolling a 6 gives evidence that you probably have a non-fair die, right, that favors landing flat. So so if you roll a 6, it's going to lower the probability. It's going to lower your the probability of your prior, right? So your posterior will be less than 1/3. It'll be in fact 0.222. Finally, we covered section 1.6, independence for three events. So we say that two events, A and B, are independent if the probability of AB is equal to the probability of A times the probability of B. We say that three events, A, B, C, are independent if the multiplication rule is probability of A, B, C is probability of A, probability of B, probability of C. And we say that three events, A, B, C, are pairwise independent if pairwise we have the following multiplication rule. So pairwise independence and independence for three events are not equivalent, as the following example shows. So here's an example where we have three people, and Bij is the event that person I and J have the same birthday. Okay, and we're going to assume that all birthdays are equally likely, any one of 365 days. So is the event that the first two, that person 1 and person 2 have the same birthday, and the event that person 2 and person 3 have the same birthday independent? I don't think so. So intuitively, if 1 and 2 have the same birthday, person 3's birthday is completely independent of person 1 and 2. So B12 should be independent of B23, but mathematically you can verify that as shown here. So for example, here the probability that person 1 and 2 have the same birthday and person 2 and 3 have the same birthday, that means that that's the event that person 1, 2, and 3 all have the same birthday, and the chance of that is 1/365 squared, because the first person can have any one of 365 days for their birthday, and the other two people just have to match that first person. So yes, is B1, B2, is B12, B23, and B13 independent? I don't think so. So right, if person 1 and person 2 have the same birthday, and person 2 and person 3 have the same birthday, then necessarily person 1 and person 3 have the same birthday. So we don't have independence between these three events. Mathematically, you can see that that we don't get the multiplication rule to work out like we need it to. So these are dependent. And finally, pairwise independence is